We've spent a lot of time looking at equations, and with good reason. Any time that you can show that two things are the same, we can write it as an equation. And if we can do that, we can use some of the techniques we've learned to solve it. And, well, depends on the situation that you're in. We can figure out a lot of things by solving equations. But not every problem that exists involves quantities that are the same. Sometimes all we know is that one quantity is more than another quantity. Or maybe it's less. Or maybe it could be the same, but more, but not less. In these kind of situations, an equation's not quite as useful. What we want to use is something else called an inequality. An inequality is a statement similar to an equation, but it doesn't use equals. So we still have two expressions, just like an equation, but instead of the equal sign in between them, we'll use an inequality symbol. Well, these are the main ones we're going to look at in this lesson. So the first one is less than. So the less than symbol, if we want to say that x is less than some number a, looks like this. So notice that this symbol has two lines just like the equal symbol, but they're together at one side towards the x, and they're open at the other side at the a. In this case, this shows that x is less than a because the small end is towards the lesser number, and the large end is towards the greater number. We also can say that x is greater than a. Now we can also write these as x is less than, but also possibly equal to a. So x is less than or equal to a is how we state that. We can also say that x is greater than or equal to a. Now, to be clear here, these don't represent x having one particular value, like it would say if we said that x was equal to a. X can be a range of different values. So to represent that, we can draw it on a number line. So for x is less than a, we're going to draw an open point at a, and we're going to draw an arrow showing the values that x can take. Now the reason we use an open point is to show that x cannot actually be a itself. It can get as close to a as we like as long as it's less than a, but it can't be a itself. For greater than, we draw this the same way, but for values greater than a, our arrow will go to the right. Now for less than or equal to and greater than or equal to, we're going to draw them the same way, but use what we call a closed point. In this case, this is to show that x can be the value a. So a is included as part of the solution set that we're describing. So if we have the statement that x is below 3, that's really a way of saying that x is less than 3. So if we want to draw what that looks like, our boundary of our solution set is at 3. It's going to be an open point at 3. And we want less than, so our arrow needs to go to the left. If x is at least -7, that means that x is greater than or equal to -7. X can be more than -7, but it can also be -7 itself. So to draw this, -7 is our boundary. We have a closed point at -7, and then our arrow goes to the right. Now, this is how we represent inequalities. But one thing we might want to do is similar to equations is to solve inequalities. Now, we're not going to end up with just a single solution like we might do with an equation. But what we can do is work out the possible values that our variable can have and describe that using an inequality symbol as well. So let's look at the inequality 2x take 7 is greater than 9. Well, let's try some values for this expression 2x take 7. So if x equals 5, we have 2 times 5, which is 10. Take 7 is 3. In fact, we can work this out for the others. So 2 times 8 is 16, take 7 is 9. 2 times 10 is 20, take 7 is 13. And 2 times 12 is 24, take 7 is... I have the wrong answer in my answer key. That should be 17. Okay, so are these greater than 9? Well, let's work with the ones that clearly are one way or the other. 3 isn't greater than 9. 13 is greater than 9. And 17 is greater than 9. Notice though, for x equals 8, our expression was actually equal to 9 itself. So no, that is not equal to 9, but I'm going to make a note that this is our boundary. This is where our expression changes from being less than 9 to greater than 9. Let's look at the inequality negative 3t plus 5 is greater than or equal to negative 1. So, negative 3 times negative 1 is 3, plus 5 is 8. Negative 3 times 1 is negative 3, plus 5 is 2. This will be negative 3 times 2 is negative 6, plus 5 is negative 1. And negative 3 times 5 is negative 15, plus 5 is negative 10. So, are these greater than or equal to negative 1? 8 is, 2 is, negative 10 is not, and lastly, negative 1 is greater than or equal to. But again, this is our boundary, because this is where the expression changes from being less to greater. Actually, in this case, it changes from being greater to being less. Let's go ahead and graph these as well. So our solution set for this one here, remember our number line is showing our variable x, it changes at 8. And then it's not true at 8, but it is true for x greater than 8. In fact, we can write that down, that x is greater than 8. For our other inequality, our boundary is going to be at t equals 2. Now that is included as part of our solution set. We see that this is true when t is less than 2. Okay, it's true for 1 and negative 1. So our arrow actually needs to go the other way. Now something interesting happens here. Do you notice that our inequality for our first one that we solved has the same direction? But our inequality for the second one actually has the opposite direction. Actually, I think that's why I messed it up in the first place, is because of that change of direction. So why do you think our first inequality here has the same direction for our original inequality and our solution? And why does the second one change its direction? Well, it actually comes down to what the variable and the expression on the left does. So here you can see that as x increases, the expression also increases. Over here, as the variable t increases, the expression actually decreases. This is where our change of direction occurs, and the reason for that is the negative that's in front of the t. In general, we need to be careful when our inequalities have a negative in front of the coefficient of the variable, because that can change the direction of our inequality. Let's look at how we could actually solve these inequalities, not by creating a table and analysing it solution by solution, but let's actually use some algebra to get to the solution directly. So, if we have same inequalities as before, so 2x minus 7 is greater than 9, we're going to take the same approach we would take if this were an equation. So, remember what we can do is to remove this take 7, we can do the inverse, which is adding 7. If we do that, we get 2x is greater than 16. Then, if we divide both sides by 2, we get x is greater than 8. Now notice we didn't have to multiply or divide anything by a negative, so nothing had to involve a change of direction in this case. So our process for solving was exactly the same as it would be for an equation. For our other inequality though, we have negative 3t plus 5 is greater than or equal to negative 1. So the first thing we'll have to do is subtract 5 from both sides. Once we've done that, we have that negative 3t is greater than or equal to negative 6. Then we'll divide by negative 3, and doing this causes our change of direction. So t is now less than or equal to 2. Let's summarize this idea for how we should solve inequalities. So firstly, whatever we do, whenever we apply operation, we have to do the same thing to both sides. That's just like we do with an equation. Now, if we're adding or subtracting, no changes of direction, so we have to keep the same inequality, or just keep the inequality. If we multiply or divide by a positive number, again, there are no changes in direction, so we have to keep the inequality. But if we multiply or divide by a negative number, that does involve a change of direction. It means the expression and the variable will have opposite directions. One will increase when the other decreases. So we have to reverse the inequality for it to make sense. So if we have 3y take 5, sorry, that's a little out of focus there. If we have 3y take 5 is greater than 10, the first thing we'll need to do is add 5 to both sides. So if we do that, we'll get 3y is greater than 15. Then we can divide both sides by 3 and get y is greater than 5. So if we want to graph this, our boundary will be at 5. It will be an open point, and our arrow goes to the right. If we have negative 8u plus 12 is less than or equal to negative 4, the first thing we'll do is subtract 12 from both sides. If we've done that, we get negative 8u is less than or equal to negative 16. Then we need to divide by negative 8. Now, we're dividing by a negative number here. And if we were paying attention before, this should be setting alarm bells off in our heads, because this is what tells us we need to reverse the direction of our inequality. We've divided by a negative number, so we now have that u is greater than or equal to 2. Again, if we want to graph this, our boundary is at 2. We're going to have a closed point, and then because this is greater than, we draw our arrow to the right. Let's look at one final example that we might use an inequality for. Ben can save $180 each week, but he currently owes the bank $630. He can afford to go on vacation once he has more than $4,500 saved in his bank account. When can Ben afford to go on vacation? So first thing we need to find is the variable. Now remember, we want to look at what the question is actually asking for to figure out what the variable is. So this is asking, when can Ben afford to go on vacation? Another way of saying that is, how much time has passed before Ben can go on vacation? So we're going to say let x be. Now, how are we going to measure the amount of time that's passed? Well, the question talks about weeks. So I think that's probably the best unit to use. So let x be the number of weeks passed. Okay, so let's write our inequality. Ben's starting bank balance is negative $630. That's what it means to owe money. He effectively has a negative balance. But he's going to add to that $180 times the number of weeks. And then what we want, well, what Ben wants really, is for this to be greater than 4,500, because that will allow him to go on vacation. So let's solve this inequality. So I'm going to copy it down so we have more space for our working. First thing we'll want to do is add $630 to each side. So if we do that, we get 180 times x is greater than, let's see, that will be 5,130. Now what this number represents here is the actual amount of money Ben needs to save for his vacation. He needs to save the $630 to pay off his debt, and then he needs to save the additional $4,500. Next, we'll divide by 180. Now, there's no negative that we're dividing by here, so there won't be a change of direction. So x must be greater than 28.5. Now, because Ben's probably saving this money each week, if we assume a normal working week, he's probably only getting paid once per week. So it doesn't really make sense to say he can go on vacation halfway through the week. So let's say that Ben can go on vacation after at least 29 weeks. Now, hopefully you can see why an inequality is more useful here than an equation. If it was an equation, we would be suggesting that there was only one point in time that Ben could go on his vacation. But because of an inequality, it shows that Ben can go on vacation at any point after the 29 weeks, not just at 29 weeks itself.